Every single day, without even thinking about it, you're basically a master of physics. Seriously, from opening a jar to riding a bike, you're constantly making things turn, twist, and rotate. Today, we're going to pull back the curtain on the science that makes all of that happen.
Okay, so think about this for a second. Pulling a sheet of toilet paper, twisting a doorknob, cranking the steering wheel of a car. They all seem like completely different things, right? But believe it or not, in the world of physics, they're all connected. And there it is. That's the secret sauce. Every single one of those actions involves what we call a turning effect. It's this fundamental idea that causes something to rotate, and physicists have a couple of really cool names for it. A moment, or probably more common, torque. And getting a handle on torque is what this whole explainer is about.
Right, so here's our game plan. We're going to start by defining exactly what a moment is. Then we'll look at a really neat special case called a couple. After that, we'll get into how all this turning stuff relates to balance and stability. We'll cover the super important principle of equilibrium. And then, at the very end, we're going to put your new skills to the test.
Okay, first things first. If we're going to talk about turn-in forces, we need a way to actually measure them. It's not enough to just say, oh, turn it harder. Physics needs numbers. It needs a formula. And that right there is where the whole idea of a moment comes into play.
So what is a moment or torque? Well, it's pretty simple, actually. It's just the product of a force and a distance. But, and this is the part you absolutely have to remember, it's not just any distance. It has to be the perpendicular distance from the pivot point. That means it's got to be measured at a perfect 90-degree angle to where you're pushing or pulling.
Let's use this diagram to really see what's going on. Just look at the picture for a second. You've got the pivot, that's the point it turns around. You've got the force, which is F, and then you have D, that's our superstar, the perpendicular distance. The bigger that force F is, or the longer that distance D is, the bigger the turning effect. It's exactly why using a longer wrench makes it way easier to loosen a stubborn bolt. You're increasing D.
That is the perfect question. Because, let's be real, the real world is messy. We're always pushing and pulling on things from weird angles. So what happens then? How do we figure out the moment when it's not a perfect right angle? Well, we don't just throw our hands up. We just have to use a little bit of math.
So let's check out this example. We've got a rod that's 45 centimeters long, and it's being held at an angle. Then there's a 15-Newton force pulling straight down on the end of it. See how the force isn't perpendicular to the rod itself? So our big challenge is to find that magic perpendicular distance, D.
And we do that with a little bit of high school trigonometry. All you have to do is take the full length of the rod, that's 0.45 meters, and remember, always convert to meters, and you multiply it by the sine of the angle. In this case, that's the sine of 65 degrees. Once you have that perpendicular distance, the hard part's over. You just multiply your force, 15 newtons, by that number, and boom, you get the moment, 6.1 Newton meters. And that's the unit we use for torque.
All right, now that we've got the basics down, let's look at a really elegant special case. Sometimes you don't just have one turning force. You have two, working together in perfect opposition. And in physics, we have a name for that, a couple. So, a couple has three key ingredients, right? The two forces have to be equal, they have to be pointing in opposite directions, and, this is critical, they can't be acting along the same line. When you get all three of those things, the object doesn't really get pushed anywhere, it just gets this pure, clean rotation.
This is the perfect example. Think about turning a steering wheel or using a big screwdriver like this one. You're applying a couple. Your hands are pushing with equal force but in opposite directions. And the beautiful thing about a couple is that the math gets even easier. The total torque is just one of the forces, times the perpendicular distance between the two forces. Simple as that.
So for this example here, it's an absolute breeze. We've got two forces, both are 30 newtons. The distance separating them is 25 centimeters, or 0.25 meters. So the torque is just 30 times 0.25, which gives us 7.5 Newton meters. You don't even have to worry about where the pivot is.
So, we know how to make things turn, but what about the other side of the coin? How do we stop things from turning? How do objects stay balanced and stable? Well, the answer comes down to finding one single super important point.
And that point is called the center of gravity. The easiest way to think about it is as the average location of all an object's weight. So for something symmetrical, like a perfect ruler or a ball, the center of gravity is right in the geometric middle. But for any object, no matter how weird its shape, if you can find its center of gravity and support it right there, it will balance perfectly. Now, how stable an object is really depends on two main things: how low its center of gravity is, and how wide its base of support is. Think about a racing car. It's got a super low center of gravity and a really wide base. That makes it incredibly stable. It's really hard to tip over. But then you have something with a high center of gravity and a narrow base, like a double-decker bus on a steep hill. It's much less stable. If that center of gravity moves so it's no longer above its base of support, it's going to topple over.
So when you see something that's perfectly balanced and stable, it's not some kind of magic. It's physics. It means all the different turning forces acting on it are perfectly canceling each other out, and they're following a fundamental law.
This right here is the principle of moments. This is the secret behind a balanced seesaw. For that seesaw to stay level, the turning effect trying to pull it down clockwise has to be exactly equal to the turning effect trying to pull it down anti-clockwise. If one side's moment is even a tiny bit bigger, the whole thing will tip. It's that simple and it's that powerful.
All right, we've talked about moments, couples, center of gravity, and equilibrium. I think it's time for a quick pop quiz to see if you've really got a feel for these turning effects.
Okay, here's the problem for you. We've got a uniform beam, it's 4 meters long, and it's pivoted right in the middle. Now we apply a force of 100 newtons straight down on one end. So, what's the moment about that pivot? Go ahead, take a second and think about it.
Did you get it? The answer is 200 Newton meters. How? Well, the force is 100 newtons, and the distance from the pivot in the center to the end of the beam is half the total length, so that's 2 meters. Force times perpendicular distance, 100 times 2 is 200. Simple as that. You've totally got this.
We have covered a lot today, from doorknobs and screwdrivers all the way to seesaws. So I'll leave you with one final thought. Now that you see the world in terms of pivots, forces, and moments, what's one everyday object that you're just never going to look at the same way again? Thanks for watching.